So next topic we have to study in YDSE is finding the expression for fringe width. What is fringe width? We have already discussed few things. For example, this is this experimental setup for Young's double slit experiment. We have two sources or a same source which is further converted into two different sources, right? By using two different slits, but for now we are considering that both of these sources are different so that we can account for the different wavelengths and different phase difference of the sources, right? Now, when there is a interference pattern right here on the screen, so what kind of interference pattern do we observe here? For example, let us say this is the middle point of the screen having a distance d from the source, and these two sources are at a distance small d among themselves. So the bright fringes and the dark fringes are of this pattern. At center you will be having bright fringe, then dark fringes both sides, right? This is how interference pattern is obtained, right? Now just a second. These blue are our dark fringes or the destructive interference, red ones are our bright fringes that are constructive interference. Now we want to find an expression for fringe width. What is fringe width here? Fringe width is how large or how thick is this particular fringe. Let it be of dark, let it be of bright, how thick is this fringe? That is called fringe width. We need to find an expression for it. For this, what we are doing, first of all, on this screen on which we are taking the interference pattern, we mark up a point. Let us say this is our point at which we are taking the observation. Let us call it point X. I was about to take it P, but P we are using for path difference, right? So let us call it point A. Let it be. All right. Now, the path from S1A would be this, and path from S2A would be this, right? So how do we write? See, what the procedure which we are going to follow right now is this. I am finding this distance, that this is a distance y from central bright fringe or from the center, and now what I will do, once I have got the distance y, I will write the value of y in terms of bright fringes separately and dark fringes separately. That is constructive, the constructive interference or maxima separately and minima separately, right? Once I have done that, I will subtract two consecutive bright fringes or two consecutive dark fringes. What I mean, suppose I have got the expression of y in terms of something. I am not going to give you the exact answer something. See, in terms of something, okay. I will put the value of n so that I will get the value for first bright fringe, second bright fringe and third bright fringe by putting different values of n. Now if I want to have the fringe width, what I will be doing, I will be subtracting any two consecutive fringes. For example, sixth bright fringe and fifth bright fringe, or fourth bright fringe minus third bright fringe. So any two consecutive bright fringes or any two consecutive dark fringes, the subtraction is going to give you the fringe width. This is the methodology we are going to follow. So for now, I want to write the value of y in terms of all those components which we have derived before. What have we derived before? We have known that path difference and phase difference for constructive interference was phi was equal to 2n pi, right? And path difference was n lambda. This was for bright fringes, constructive interference, right? And for destructive interference, what did we have? This phi was equal to 2n minus 1 pi, right? Because for all those angles when cos phi was minimum pi, 3 pi, 5 pi, 7 pi, and similarly the path difference, that was phase difference, path difference was equal to 2n minus 1 by 2 lambda. These were the four values. These were basically the conditions which we derived in the last derivation, right? Now let's proceed. We'll start with the path difference. Path difference. Path difference P is equal to which light ray has the lengthiest path right now, where this is S2A, right? So path difference is S2A minus S1A. Okay, we are going to write the values of S2A and S1A separately, and then we'll put it in this formula. Let us say this is equation 1. For S2A, I have to draw complete this right triangle so that S2A would be the hypotenuse. Similarly, for S1A, I'll be doing the same thing. So, what other distances do we have now? This is the centermost part, okay? According to my diagram, it doesn't look like, but this is the center part. So, this distance would be d by 2. Similarly, this distance will also be d by 2. Alright. So, S2A from this right triangle would be under root of this square, which is d square, plus this square, which is y, plus this much distance, d by 2 ka square. So, S2A is equal to under root, I'll write the under root, that is like this, right, d square plus y plus d by 2 whole square. Done. To solve such kind of expression where you have complicated powers, what you do, you use the binomial theorem. Application of binomial is very simple. What you do, you just make the first term 1 unity, and then whatever the power is, you can place the power in front of the second term. To make the first term 1, what we can do, we can take this d square common out. It's like this. How we do this? I have taken d square 1 plus 1 upon d square y plus d by 2 whole square right. See, multiply d square in the bracket, what will you get? D square into 1 is this term, d square into this is this term. So, we have not done anything complicated yet. The only thing which might be wrong in this whole equation would be the application of the this thing, brackets, because square brackets are supposed to be here and the curly brackets are the biggest brackets, right? But again, this methodology is followed in different books in different ways, so that's hardly matters. So now I am taking d square common out of the under root, that will become d. So now I have d, then this bracket 1 plus 1 upon d square y plus d by 2 whole square under root. This is the expression I am left with. Now applying binomial theorem, what will I have? I'll have d, the root, this power goes in front of second term if the first term is unity. This is simple application of binomial theorem. So 1 plus 1 upon d square, 1 by 2 goes here, so 1 upon 2d square y plus d by 2 whole square. So this is the ultimate left variable for S2A. Okay. Similarly, in case of, now listen carefully, now similarly in case of S1A, that is this, S1A would be under root this square, which is d square, plus this much. This much is what? This much is y minus d by 2 whole square. So instead of plus, I will be using minus here. So everywhere it will be minus. So S1A would be, S2A is this, S1A is what? D, I am writing similarly, d 1 plus 1 upon 2d square y plus d by 2, no, y minus d by 2 square, right. This is these are two expressions for S2A and S1A. Now I have to subtract it, whatever the answer would be, I will make it equal to the part difference which you already know, we have derived it yesterday. So I am rubbing it all. If you want to note it down, you can pause the video. Now instead of S1, S2A, now I have already written it, so I am not writing it again and again. So what I will do, therefore P is equal to, you guys would be writing, putting these values, let us say, let it be equation 2 and equation 3, right. So what you will be writing, putting values from equation 2 and 3 in equation 1. So P will become, first of all, this minus this, d 1 plus 1 upon 2d square y plus d upon 2 whole square minus, okay, minus d 1 plus 1 upon 2d square y minus d by 2 whole square, right? That's all. So now we'll follow the simple mathematical terms. Just a second, I'll be requiring a lot of space now because I don't want to rub the this diagram. So moving on, multiplying d, we will get d plus 1 upon 2d y plus d by 2 square minus d minus, right? This was plus multiplied by minus, it will become minus 1 upon 2d, right? Not d square, because when I multiply d with d square, 1d gets cancelled out, right? So 1 d upon 2d square, 1 upon 2d, y minus d upon 2 whole square. Again you can cancel out this term and this term, and from these two terms, from this one and this one, you can take out 1 upon 2d common. So 1 upon 2d y plus d by 2 whole square, this is square, minus y minus d by 2 square, right? For this term I can write 1 upon 2d, this will become y plus d by 2 plus y minus d by 2 whole multiplied by y plus d by 2 minus y plus d by 2. What did I just do? This is a square, this is b square. What is the formula for a square minus b square? A plus b into a minus b. So what are the terms getting cancelled here? D by 2 and y. Here you are left with y plus y, which is 2y, and d by 2 and d by 2, which is d. So again rubbing all, part difference is this. Path difference is 1 upon 2d multiplied by y plus y, 2y multiplied by d by 2 plus d by 2, which is small d. Alright. So path difference is y small d upon capital D. This clearly implies that the distance which we were looking for in terms of n is p capital D by small d. See, how do we proceed now? Because our ultimate goal is to find an expression for fringe width, how much broader this, or how much, what is the breadth of the fringes we have just obtained. So this is the expression from which we will do two things separately, for maxima or what? For constructive interference. For maxima or constructive interference, P is equal to, where this thing, P is equal to n lambda. So y becomes n lambda capital D upon D. This is an expression for the position of bright fringes from the central one. Now we know that n is equal to what? 0, 1, 2 and so on for maximas, right? Put n equal to 0 in this equation, so y equal to 0 from center, that means central most itself is the bright fringe. Now when n equal to 1, that is 1 lambda d by d, so I will get this much distance. When I put n equal to 2, I will get first, second, that is the second bright fringe. N equal to 3, third bright fringe. So this is how we can obtain different values. y1 is equal to lambda d by t, y2 is equal to 2 lambda d by d, y3 and so on, 3 lambda d by d. So how do we find the value of what? The fringe width. Fringe width, I already told you, if I want to obtain the value of bright fringe, the width of the bright fringe, what I am going to do, I will be subtracting two consecutive fringes. For example, I will be doing, either I can do y3 minus y2, or I can do y7 minus y6, or I can find y11 minus y10. Getting my point? Just try to subtract any two consecutive fringes. What I will be doing, I am going to do it for the generalized version, that is n. So yn fringe width, I will write it like this, fringe with beta is equal to yn minus yn minus 1, like the two consecutive terms. Yn would be n lambda d by d and yn minus 1 would be n minus 1 lambda d by d, right? Multiply it, n lambda d by d minus n lambda d by d, minus into minus plus 1 lambda d upon d. So this whole term gets cancelled out and you are left with beta is equal to lambda d by d. So I'll write it somewhere here. Therefore beta is equal to lambda d upon d. This is the expression for fringe width in terms of wavelength, the distance between source and screen, and the distance between two sources for bright fringes. What if for dark fringes the fringe width is a bit different? It might be according to formula, so you can do it for that separately. For minima, P was equal to 2n minus 1 by 2 lambda. Therefore, y is equal to 2n minus 1 by 2 to what? That is P. 2n minus 1 by 2 lambda. So putting value of P here, 2n minus 1 by 2 lambda capital D by small d. This is the formula for position of any dark fringe in terms of n. So if I'll put the value of n, now we know that for dark fringes n did not start from what? 0, n started from 1 and so on, right? So first dark fringe, which is this and this, first dark fringe will be n equal to 1, 2n minus 1 is 1, 1 by 2, that is y1 will be equal to 1 by 2 lambda d by d. Then second would be 3 by 2 lambda d by d, then 5 by 2 lambda d by d, and so on. So how do we find the expression for fringe width? Again beta dash, let us call it beta dash because there is a possibility that beta and beta dash might be different. So beta dash would be, take the generalized version, instead of just subtracting any two consecutive, beta dash would be yn minus 1. And my friends, if you will do that properly, then what the answer you are going to get is again lambda d upon d. That means the width of fringe in case of bright and dark fringes are always equal in case of interference, and this we have done and derived and proved from Young's double slit experiment. Alright, so this question, this whole thing can be asked to you in very different formats. Now in the end you can write it, you can conclude this derivation like this. Therefore beta is equal to beta dash, which is equal to lambda d upon d, and fringe widths are equal in case of maxima and minima. Alright.